Welcome to the Explainer. Today we're going to mess with your head a little bit, challenge some of your most basic ideas about how reality even works. We're diving deep into Albert Einstein's theory of relativity. And trust me, this is an idea so big, it completely rewrote the rulebook for space, time, and even gravity itself.
And it all kicks off with a question that sounds, well, almost deceptively simple. But chasing the answer to this one little question, it sparked a scientific revolution. It literally shook the foundations of physics, foundations that had been solid for more than 2 centuries.
Okay, so to really get just how big of a deal Einstein's work was, we've got to rewind a bit. Let's go back to the late 1800s. Physics was in a real bind back then. It was facing this huge contradiction. Basically, there were 2 sets of rules for how the universe worked, and they completely disagreed with each other. They just could not both be right. So on one hand, you had the physics we all kind of intuitively understand, right? The stuff Newton figured out. If you're on a train that's moving and you throw a ball forward, the ball's speed just adds to the train speed. Simple. Makes perfect sense. But then there was this other thing. A whole bunch of really smart experiments, like the super famous Michelson-Morley one, started showing something really weird. They found that the speed of light is always the same. It doesn't matter how fast you're moving towards it or away from it. It's like the universe has this one single cosmic speed limit that nothing can break.
Just try to wrap your head around that for a second. Imagine you're in a spaceship, okay? And you're zipping along at half the speed of light. If you flick on your headlights, the old rules, Newton's rules, say that light beams should be moving at 1.5 times the speed of light. But it's not. The experiments proved it. It still travels at exactly the speed of light. This was the problem. This was the big crisis, a paradox that was sitting right at the heart of everything they thought they knew.
So you've got the entire physics community just scrambling, trying to find some mistake in these experiments. But then this young patent clerk, a guy named Albert Einstein, comes along with this incredibly bold, radical idea. He basically said, hey, what if the experiments are right? What if the speed of light is the one thing that's true? And the problem is actually with our understanding of space and time themselves. And so in 1905, he drops his theory of special relativity on the world. And it's all built on these 2 beautiful, simple ideas. First, the laws of physics work the same for everybody who's moving at a constant speed. And second, and this is the real game changer, the speed of light is the same for everybody. That's it. From just those 2 ideas, this whole new, kind of strange, but absolutely incredible vision of the universe started to emerge.
Now, to help us regular folks get our heads around this stuff, Einstein loved to use what he called thought experiments. They're brilliant, so let's try one out that he actually described in his book. Just picture this. There's a really long train, and it's just cruising along at a steady speed.
Okay, so what does this all mean? Well, this simple little story completely shatters an idea we all just assume is true, the idea of at the same time. See, for the person standing on the ground, those lightning strikes are simultaneous. But what about the person on the train? Because they're moving toward the light from strike B, that flash of light gets to them first. For them, the events did not happen at the same time. And that's the whole point. It proves that the very idea of now is relative. It actually depends on how you're moving.
So here is the absolutely stunning takeaway from all this. If the speed of light has to be the same for everyone, then something else has to give. And that something else is space and time. They can't be absolute. To make the math work, to keep that cosmic speed limit in check, the universe literally has to bend and stretch reality. So for someone moving really fast, time itself has to slow down. We call that time dilation. The space they're moving through actually has to get shorter. That's length contraction. And then for the grand finale, Einstein showed that mass and energy are 2 sides of the same coin, giving us probably the most famous equation in history, E equals mc squared.
But here's the thing. As amazing as special relativity was, it had a hole in it. It only worked for things moving at a nice, steady speed. It didn't have anything to say about acceleration, speeding up or slowing down. And it left out the biggest force of all, gravity. So Einstein knew he wasn't done. He spent the next 10 years just wrestling with this massive problem. And then he had this breakthrough, a moment he later called his happiest thought. Imagine this. You're in an elevator, but it's way out in deep space, far from any planet's gravity. If that elevator suddenly starts accelerating upwards, what would you feel? You'd feel your feet get pressed to the floor, right? It would feel exactly like gravity. And that was it. Einstein realized you can't tell the difference between feeling gravity and feeling acceleration. This idea, the equivalence principle, was the key that unlocked everything.
And that realization led him to an even bigger, even crazier question. What if gravity isn't a force in the way we think of it? What if big things like the sun aren't actually pulling the Earth through space? What if they're actually bending and warping the very fabric of the universe itself?
And that incredible idea, that became the heart of his masterpiece, which he finished in 1915, the theory of general relativity. It completely redefines gravity. It's not some mysterious force reaching across space. Now, gravity is the shape of the universe. It's the curvature of this four-dimensional thing he called space-time. Yeah, visuals like this one are a huge help in trying to picture this. The classic analogy is to think of space-time like a giant, stretched-out rubber sheet. Now, if you drop a heavy bowling ball onto it, say a star, what happens? It creates a big dip, a curve in the sheet. That's the core idea. In Einstein's universe, mass literally tells space-time how to curve. So if mass tells space-time how to curve, what does curved space-time do? Well, it tells matter how to move. So going back to our rubber sheet, if you roll a little marble, say the Earth, near that big bowling ball, it doesn't get pulled in, it just follows the curve. It's trying to go in a straight line, but the space it's moving through is curved. And that path, that straight line through curved space, that's what we see as an orbit.
Now, this new picture of gravity wasn't just a neat idea. It made some absolutely wild predictions. It said that the stronger the gravity, the slower time itself would tick. It said gravity could actually bend a beam of light. And it predicted things that sounded like they were straight out of science fiction. Things like black holes and actual ripples in the fabric of space-time, which we call gravitational waves.
Okay, so I know what you might be thinking. Black holes, curved space-time, this all sounds super abstract and cosmic, right? Like it has nothing to do with us here on Earth. But you actually rely on Einstein's theories every single day, probably without even realizing it. So what's with this number? 100%. That's the percentage of GPS systems, the GPS in your phone, in your car, that would be completely and utterly useless if they didn't account for relativity. Here's how it works. The clocks on those GPS satellites floating way up in orbit are being hit by two different effects from relativity. First, because they're moving so incredibly fast, special relativity tells us their clock should actually run a tiny bit slower than ours down here. But at the same time, they're in a weaker gravity field than we are, so general relativity says their clocks should run a tiny bit faster. To figure out where you are, your phone has to constantly correct for both of those things happening at once. And we're not talking about tiny, insignificant corrections either. If we didn't account for relativity, those little timing errors would add up so fast that in just one day, your GPS location would be wrong by about 10 kilometers. That's more than 6 miles. The whole system would be completely broken. So think about it. Einstein totally changed our picture of the universe just by being brave enough to question the stuff everyone took for granted, like what time is or what space is. It's just an amazing reminder that our common sense is really just based on our own tiny, limited experience of the world. And it really makes you wonder, doesn't it? What other obvious truths that we all believe today are just waiting for the next genius to come along and show us we've had it all wrong?